Thank you. Well, at this stage in my career, I'm trying to figure out whether I have room for one more arrow in my back or not. Since there was a miscommunication and I didn't submit an abstract, I decided that I would use this session title as the title for my talk. So all of you are familiar, I'm sure, with the DOE's GPU accelerated platforms. And so we have the Frontier system based on AMD GPUs. We have the Aurora system based on the Intel Data Center Max GPUs. And then we have El Capitan based on AMD's APUs. And so at a high level, you know, everybody's doing GPU accelerated computing, but at our level where we write performance tools, these things are completely different, okay? And so the concerns for each of the systems are completely different. The software stacks are different. And so it's a major problem. And so this is the landscape for the exascale systems, but beyond these systems, there's a lot of innovation going on in hardware these days, and CPUs not only have, you know, one kind of cores, there's like energy efficient cores and performance cores, and sometimes both. They have acceleration engines for data movement and data compression, vector units, all sorts of things. On GPUs, the AMD and Intel use a SIMD programming model. NVIDIA GPUs use a SIMT programming model. And then there are these other architectures like the Cerebras wafer scale engine, the Samanova data scale. There's a Stencil tensor accelerator being constructed out of RISC-V at Fraunhofer in Germany. And so, you know, there's a very rich landscape beyond just the things that we're using for GPU accelerated computing that people are using for AI or other things. And so this hasn't quite sort of bubbled up to the surface in our project yet, but we're just like looking at this over the horizon and thinking that, you know, we're going to have to think about tooling for this very unconventional set of things. And then on these systems, of course, there's memory, and sometimes it's DDR memory, sometimes it's high bandwidth memory, sometimes it's both, and there's deep memory hierarchies, and the CPUs have one memory hierarchy, the GPUs have another memory hierarchy, APUs sort of straddle. It's like 1.5 memory hierarchies. And we have interconnect between chiplets, between nodes, between the devices on the nodes. There's explicit copies, there's implicit copies between devices with page faults. There's one-sided communication, two-sided communication, lots of different things going on. And, you know, we're trying to build tools to just monitor all of it, and it's all different for every vendor. So, you know, there's a lot going on. So some high-level performance questions you might like to ask. You know, what's an application doing? What resources does it have at its disposal? How well is it using those resources? Are you using only one GPU tile on a node? Are you using all of them? Are you using all of the cores in your system? Did you intend to, or did you leave them idle purposely because you were only using like one core to launch things on each of the GPU tiles you have? Are there opportunities for improvement? Is there adequate parallelism in your program to keep the data parallelism in the GPUs occupied? What's the rate limiting factor? Is it compute limited, communication limited, I/O limited, data movement limited? So is communication a problem? Is there too many excessive number of small communications? Are there lots of large communications? Is there network congestion? These are all things that people want to know. Are there opportunities for better scheduling or mapping? Maybe you've bound your MPI ranks to the wrong GPUs, which is a common problem, and so your data movement is extra costly. Are there notable inefficiencies in your application, like imbalance or serialization or contention? Do you have underutilized functional units in your CPUs or GPUs? Are you thrashing the memory hierarchy? Is there a lot of exposed memory latency? There's lots of questions. I mean, I'm hardly scratching the surface. You know, for grins, you can ask Google Gemini about what it's like monitoring just the kinds of cores I have in my laptop here, where I've got performance cores and energy efficient cores. These kinds of systems are enormously hard to monitor because they don't even have the same performance counters in the different kinds of cores. And if your computation is in a thread that's moving back and forth, what are you really monitoring anyway if you don't have the same counters on the different kinds of cores? So the monitoring is quite a hard problem. So some measurement challenges for these GPU accelerated systems. We've got extreme scale parallelism, and what that means is that since there's extreme scale parallelism in the application, if we have any serialization within our tools, then that's going to disrupt the parallel performance, and we don't want to hurt the performance by trying to measure it. And so inside our tools, we end up building highly concurrent data structures, building even some weight-free data structures for pushing data back and forth, like measurement data back and forth between monitoring threads and the application threads that are recording them. There's frequent GPU kernel launches, and so with the measurement infrastructures we're using, the vendor measurement infrastructures will monitor the GPU operations as they're being launched. And therefore, the overhead has to be low. Otherwise, if you're launching 100,000 GPU operations in a short period of time, you can end up with an enormous measurement overhead if you're not careful. There's also multiple measurement modalities that we're using inside tools. So we're using sampling on the CPU in order to measure what the application is doing. For the GPU, we're tracing the APIs using infrastructure provided by the vendors. And so every time an operation is initiated, we get asked to note it, and we can assign a correlation ID to it. On the GPUs themselves, I've been instrumental working with NVIDIA and AMD and Intel over the years in getting them to add hardware support for instruction level performance measurement that's known as PC sampling. There's also tools for binary instrumentation. NVIDIA has NVBit and the compute sanitizer. Intel has GTPin. And so for some things where you want to measure in detail, sometimes doing binary instrumentation is the best way to find out, whether you're using all of your SIMD lanes or things like that based on the data that you're running through your program. So the tools can only measure what the hardware can monitor, and so there's hardware counters in the CPU, the GPU, the network interface, the network fabric, and there's support for instruction level performance measurement on AMD's MI250X GPUs on Frontier. They managed to build support for PC sampling, but it's all done in software. They freeze the GPU and then they scrape PCs out of it. So they've built hardware support for doing PC sampling on the GPU and the MI300As that are in the El Capitan system at Livermore, and NVIDIA has this sort of support in their platforms since their Maxwell GPUs, and Intel now has it in their Ponte Vecchio GPUs. And when you have the hardware support for performance measurement, not only can you find out that what instructions are executing, but you can also find out information about which instructions stalled and whether they stalled for the memory hierarchy or whether they stalled for the pipeline or things like that. These are the kinds of things that we've gotten used to having on the CPUs for many years. But what we're getting is sort of a bare bones effort on the GPUs now. So while we can find out that we're waiting for the memory hierarchy, we can't tell whether we're waiting for the L1 cache or the L2 cache or the L3 cache or where the data is being served from. And so what we get is sort of a limited picture. But it's a lot better than just saying your kernel was slow, right? So the tools that my group builds, so my group builds the HPC Toolkit performance tools, and so what we do is we use these measurement interfaces that are provided by the operating system. So we use the Linux perf events measurement subsystem to measure on the CPUs, and then we have to use the monitoring libraries that are built by the vendors. And so the GPU monitoring libraries only monitor what the vendor includes, and so that can be a problem if they don't monitor everything. So one of the issues that came up on Frontier is we were seeing some weird delays, and we discussed with AMD, and they said, oh, that might be GPU scratch space reclamation. And we said, oh, so how long can that take? Well, it can take a while. Can we measure that? No, you can't measure that. And so, this turned into a conversation. Well, like, what are all of the things that like page migration and things like that were invisible, and they needed to add APIs for us to see them because they don't allow us to kind of run our fingers through their IP and get down, and interact with the hardware directly. So we've got this interface that provides a level of abstraction to us. So what about the usability of these systems? Well, I think that Edvard Munch said it the best. This is his pastel known as the Scream. It kind of applies to not only his mental state at the time, but our exascale experience, some might say our current political climate. So there's, in terms of basic usability concerns for the exascale platforms, there's just an overwhelming sophistication and complexity of the compute nodes. Sophistication for delivering performance, but honestly, it's a lot of complexity as an application developer. And the fact that all of these systems differ between even between generations from the same vendor are quite different under the hood. That if you really want to get the most out of these systems, it's an enormous amount of effort. And then from the tools perspective, the overwhelming complexity of the applications, there's often over 100 shared libraries used by the applications, and there's lots of embedded GPU binaries. And the applications themselves are doing all sorts of things. Like these exascale applications are using communication systems like UCX, and UCX just believes that, it can override any call to mmap where you're mapping memory, and then put locking, like in their wrapper around it, they can put locking. And so if our tools use mmap and we're calling their wrapper, then that can like deadlock the whole thing. And so really what we need is to have separate namespaces where the things that we put into the address space of the application can't see, and that we're not affected by what the application puts in the address space. And so there are tool infrastructures like Intel's GTPin uses a separate namespace. And what this means is that when you're running an application, there might not be just one copy of libstandard C++. There might be one that comes in with a tool framework like GTPin, where Intel is compiled with one kind of compiler, and then you've compiled your application with another kind of compiler. And if you have these two C++ libraries in the same application, if they're not in separate namespaces, then the whole thing just falls apart. And so this has kind of become something that we're trying to move to, is to put our tools in a separate namespace instead of trying to just protect all of the things that we're using and make sure that we rename symbols so that they're not going to interfere with the application. And so the right solution is to use this protected namespace. But that adds a layer of complexity. I'll get back to that in a moment. So can I launch my application at a large scale? How many people have launched run things on the exascale systems on more than 2,000 nodes? Anybody have trouble doing it? Trouble launching your applications? Getting the MPI times out before your application starts executing? Yes, I see a number of nods. It's really painful. And so without help, the dynamically linked applications, which are the typical standard where you have your application, you have a separate set of libraries that it uses, they all get loaded into the address space of each of the MPI processes as the application gets launched. But what happens is there's a load library path that says these are the places where you might find the libraries. And so for each of the 100 libraries in the system, you might look in 100 different places and say, is it there, is it there? Thank you. And so you end up thrashing the file system. And so a tool called Spindle has been built at Lawrence Livermore. There's something called SBcast on Frontier, which is a second-rate solution, and there's nothing on Aurora. And so launching at scale on these systems is hard. When you add tools to the picture, it's even harder. So some operating system obstacles to tool development. So we have to track dynamic library loading and intercept certain functions to understand when threads are created or when or when they die. glibc provides a powerful interface called LD Audit for this purpose. In 2021, it was completely broken. We wrote a manifesto. We started a global pressure campaign to get Red Hat to fix it. We had to get all of the national labs to submit premier complaints for Red Hat to pay attention to any of these issues, because Red Hat, like they decided that their libc team were saying, we don't want to be working on LD Audit. Like we have our own priorities for development, right? And so in 2025, they've fixed a lot of these things. The dynamic loader is still fragile. There's many quirks where there's certain functions you can't call in software that's using this interface because the glibc library has not been fully loaded yet. So it's a really kind of quirky environment to work with. There's newer and better versions that are available upstream, but they're not available on the HPC platforms. And so this is like a continual struggle to just get the software infrastructure that we need. It might surprise you to know that there's like no safe implementation of thread local variables for either tools or applications on these systems. That thread local variables that you might use in your programs, they're not async signal safe, so we can't use them in our own tooling. And you might think, well, there's always pthread keys. It turns out, since 2019, there's been a bug reported that pthread keys don't work with multiple namespaces. And so we're trying to deal with these complex applications, and we don't even have the rudimentary tools. All right. So that's a little bit about the landscape. So let me say a little bit about our tools. So we built these HPC Toolkit performance tools that collect profile and traces of unmodified CPU and GPU accelerated applications. They work with a lot of parallel programming models, a lot of different languages, and all of the major processors, x86 power, ARM, and each of the vendor GPUs. And so HPC Toolkit was designed to be easy to profile unmodified applications with relatively low measurement overhead, with the understanding that we can't control the measurement overhead of the vendor infrastructures, designed for a broad audience for application developers, framework developers, runtime and tool developers like ourselves, and it supports measurement and analysis of data at the full scale of these systems. So our tools, you have HPC Run, which will launch the tool. So when you launch something with, say, MPI, then you'll just say, instead of saying MPI exec my application, you'll say MPI exec with all the parameters, and then say HPC Run your application with the application parameters. And so that'll collect profile files, and optionally you can collect traces as well. It'll also record the binaries that are injected into the GPUs, and then post-mortem we have this tool called HPC Struct that we use to analyze the application binaries from the CPU and GPU, recover program structure information, the mappings between machine code and the source code, and then we have a tool, HPC Prof, that combines this, and then an interactive graphical user interface. So at runtime, we're doing call stack unwinding to figure out how to attribute code to where costs are being incurred. And so this might mean that when you get an interrupt on the CPU in some routine C that's called from B, that's called from A, that's called from main, we unwind this call path, and then over time you end up with this tree that has weights in it, where the weights indicate like time or cache misses or GPU operations. And so we're fitting into this tree-based data structure not only information about the CPUs, but also information about your GPU execution costs. So we have a graphical user interface that shows it relates performance to the source code. The cool thing about our interface is that with the benefit of the binary analysis, we relate things to function calls, to inline code, inline templates, outlined OpenMP loops, and loops. And then when we collect profiles, we're collapsing out the time dimension. And so in order to understand the temporal behavior of the application, when we collect one of these call paths as we unwind, what we do is we unwind at time t and time t plus delta t and t plus 2 delta t. So we have a series of call paths for every thread running on one of these platforms. So hundreds of thousands of threads, and then we also get these call paths for the GPU operations. Then what you end up with is a trace that might look like something like this, where we have MPI ranks, OpenMP threads, GPU trace streams on the vertical axis, time is on the horizontal axis. There's a depth view at the bottom that shows the history of the calling context across the thread or GPU stream. that's marked with the cursor here. And then and this call stack pane shows a full call stack that applies to the particular thread or GPU stream where the crosshair is, and the colors here indicate what's going on. So the colors are like the procedure that's being executed by the particular thread or rank. So this isn't this applies. This is the call stack that applies at this point. It's not a key for this figure. So so what can we do with this? I got a few minutes. So there's an ECP project called Exawind, so it was modeling turbine wake formation, and then over time, as you're measuring more of this, then the wakes get very complicated. Of course, they're not just interested in monitoring a few turbines, they're interested in monitoring a whole wind farm. And so they had a simulation code for this called Exawind. They were running it on Frontier. They collected information with HPC Toolkit. They collected traces on 64K MPI ranks and 8K GPU tiles for about 17 minutes. And all the red over here is MPI waiting time. And so after some consultation with the folks in the Center of Excellence and the folks at Oak Ridge, they decided that this was all due to the fact that they were using non-blocking send and receive, and they replaced it with I-alt-all-V, and you can see that the MPI communication just disappeared. And so John Rood, who is one of the principals behind this, said that they improved their large-scale performance by 24x based on the insights. And the important thing was them being able to measure it at scale. It's a complicated application because it's coupled where some of the MPI ranks are doing block-structured AMR on the GPUs, and then all the rest of the CPUs are doing unstructured meshes, monitoring around the turbine hub. And so it's a coupled application running at large scale. And so the thing that was important to them is that we didn't get in their face with their build process and whatnot, where they're building this incredibly complicated piece of software. All they had to do was launch it. So some other things, this is from a recent hackathon where they were monitoring a code called Pele LMX. It's a low Mach number. They were doing computational chemistry of fuels burning, and you can see over here that there's imbalance. And so after they saw this with our toolkit, they talked to the folks in Amrex and were able to rebalance the load and got a 60% improvement on Frontier. We've also used the ability to do this instructional level performance measurement and found that there are costs that are incurred due to the way that lambda capture was used for a structure instead of passing in constants, and that by fixing the way that the lambda capture was done for this one function, it improved the entire performance of the program by 4%. I mean, that's not an impressive thing, but it sort of shows off the ability of our instruction level attribution to understand some of these subtle issues. Okay, I'm finishing up, Christian. So we collected large-scale traces on Frontier, and this is what we saw over time. You notice that there's all these wavy delays. This is lamps. This is a very SPMD application, and when it was running with kernels launched at a very fine scale, we ended up with all of these propagating delays in the network. And so the question is, what's this about? Is this congestion? Is this GPU scratch space reclamation? Is the network delays a symptom, or are they the cause? We didn't have enough time to run on Frontier before it turned into it became generally available, and so we never identified the root cause. But there's creepy behavior going on underneath. So we've built some capabilities for analyzing things at large scale. We've built some capabilities for scraping the data out in Python so that you can pull it into a Jupyter notebook. This is the second to last slide. So we also are working on some things to look at the performance inside complex kernels. And so this is from the Quicksilver kernel at Livermore. And so this is a trace inside the kernel collected with binary instrumentation. And what you can see is there's massive load imbalance, and all of the white is idleness. And so, in fact, there's a lot of idleness inside the execution of this kernel across the system. So there's some open issues for the GPU performance measurement. AMD has some software quality issues. NVIDIA and Intel, well, okay, so Intel, I will say, they have a very significant issue with respect to measurement. Their GPU binaries differ across every MPI rank. It's untenable. We can't record millions of binaries. We've reported this to them in October. They're working on it. So some issues in general. Can we develop some useful top-down models for analyzing GPU performance? There's hundreds of counters. It's very hard to understand exactly what's going on. How can we best use PC samples to get insight into performance? How can we best use hardware counters to monitor and analyze communication in the communication network? How can we best gain insight from these large-scale measurements if we're scraping the data out and pulling it into like a Jupyter notebook? What are the strategies that are going to shed insight onto like the delays that we're seeing? And can we use LLMs to interpret our performance data? So I think what we have right now is a very difficult problem to understand what's going on with these systems. And we're trying to build the tools, but we don't quite have the infrastructure we need for it.
Thank you, John.
Hello.
Thank you, John. That was interesting. We have maybe time for like 1 or 2 questions while Chris is getting set up. Talk.
Is the Quicksilver plot, like, is it blocking on memory accesses or something, or is it a bottleneck you can actually fix, or do you know?
It is. So this is using NVBit and looking at basically the trace of calls within each of the threads on the GPU. And what you see actually is the amount of work. It's not just blocking, but it's the amount of work that's happening in the different GPU threads differs. Okay. We're not entirely sure why, but the behavior is sort of surprisingly irregular.
Second question while Chris is still fiddling.
I'll buy Chris some time to get his computer working. I might come back to this later in your panel, but one thing I noticed, is there any thought about tracking the dynamic range of operands? Because you're worrying about a lot of, can we eke out X%? Are we doing this? The hardware is going, if you can decide you can get away with FP16 instead of FP64, FP32, you get enormous wins compared to a bunch of other stuff. So, or even more so. So, if you can understand, can you use a common exponent, etc. Yes. So, are you tracking that, and are you getting any help from the silicon vendors to do so?
So, what I would say with respect to that is, in order to track the values on GPUs, you actually need to use binary instrumentation for that, because you have to get in the middle of monitor every load store. And so one of my former students, Karen Zhou, built something called GVProf that actually, the V stands for values, so it's doing value profiling, and you could look at the dynamic range of the values and see that, in fact, you're using a 64-bit int and you're only using 4 bits of it. So you could do some of those things. You could detect redundant copies. That capability is not part of our full tool set. Okay, it's very important. I agree.
Very good. Thank you.